This conference will now be recorded.
Again, good afternoon, everyone. Tim Raibley of HDR. Today's webinar series for our Vision 2020 webinar is presented discussing anaerobic digestion. Two presenters today, Jim Dunbar of Lystek and Tej Gidda of Ph.D. Jim is a general manager for California's operations of Lystek International. He's a professional engineer with more than 25 years experience in the solid waste and liquid treatment industry. Lystek specializes in providing solutions to biosolids and organics management. They built a facility in Fairfield in the mid-2016 era that they've been using a patented thermal hydrolysis process to produce basically a Class A biofertilizer. They'll be discussing that and other things today. The facility that they've used there has been a research springboard for the various other things that company's been working on. Tej is a Ph.D. P.Eng, Canadian, and his work has really been in the alternative waste management industry. He's currently GHG's global leader for future energy, focusing the firm efforts on transitioning into energy systems towards lower carbon future. So pretty relevant given California's interests. He has significant engagement in the alternative waste processing space with a focus on biological treatment of organics and such as biosolids processing and anaerobic digestion. So Tej will be talking on selecting digestion technologies. So now without further ado, Jim, we'll be hearing from you.
All right, thank you very much, Tim. Certainly is a pleasure to be invited to speak at this webinar series. The topic of anaerobic digestion is one that is certainly coming more into vogue, certainly in the last few years, both driven by technology advancements and legislation. So we'll get started. Brief title is the organic waste digestion at a pilot project that we've undertaken at the Goleta Sanitary District. So next slide. So a little background, we're going to go over a brief overview of the co-digestion capacity that exists in California based on a recent study that was done. Pluses and minuses of using anaerobic digestion, and a little specific project overview of the Goleta project, and then continue in with some of the results that we've gained to date and ongoing, and what are we doing now and what are we going to do in the future, specifically as our technology improves and the legislation becomes a little bit more in effect. Next slide. So kind of a busy chart here, but the basics information to be taken away from this is that 2 years ago, the state of California undertook a survey study of wastewater treatment plants throughout the state to try to gauge what the anaerobic digestion capacity is. And this was built around most recent legislation focusing more on solid waste handling ability as to how organics were going to be diverted or removed from traditional outlets such as landfills, and where could it be processed, certainly in the short term, medium term, and what would be done in the long term. So the takeaways from this is certainly on the far right side, you can see the amount of material that's looking for a home or will be looking for a home in the next couple of years, over 3 million tons per year. And that is a recurring 3 million tons and more every year as we go on. The colored chart in the center kind of speaks to the study that was done. And whereas anaerobic digestion is certainly available, and it has been reported to be available for many years, it's those infrastructure components leading up to it and the back end of it. So for example, yes, you may have anaerobic digestion capability, but if you don't have receiving stations or processing facilities to handle organic waste, capacity isn't much value to you. And on the back end, unless you have utilization components such as either flaring, cogeneration, or some other transformation technology, generating biogas for the sake of generating biogas is really not an economic win for anybody. So you can see some of the key components there that were highlighted is that, certainly receiving stations are definitely on the short term, and positive basically conversion factors also. Next slide. So what was the benefits of looking at wastewater treatment plants, also acronymed as water resource recovery facilities? Well, they do exist. There's quite a few of them. There's hundreds of them throughout the state. They do tend to be located for each community, or certainly large communities having more than one. They do have, a tradition of handling organic waste already, but in a much more liquid and dilute state. And now the ability to maybe take a more solid concentrate or a blended concentrate rate is becoming more in the eyes of certainly the engineering side and the solid waste side. And why also at wastewater treatment plants? Many of them have anaerobic digestion. The vast majority of large wastewater treatment plants have digestion as a means of solids management to reduce the overall amount of solids generated and to be shipped off site. The resultant gas, while in the past maybe wasn't viewed as a real value to wastewater plants, it is becoming much more important as a cogeneration or fuel source, especially given some of the power outages or power shortages that have been prevalent throughout the state in the last couple of years. So there really is a look towards maybe maximizing that for the benefit of the treatment plant and then maybe also back to the grid. But like any good thing, there's always potentially a downside. Wastewater treatment plants, like I said, traditionally taking a much very dilute liquid waste stream, are now going to be challenged to take materials that maybe are not in their wheelhouse. A lot more contaminants, a lot more solid content than maybe what they're used to. And maybe a solid content that is not really made for wastewater treatment. So it needs to be looked at as to, if you're looking at an organic waste stream, will it be able to be handled at a anaerobic digester? And we can think specifically of leafy or fibrous materials that take a longer time to break down. Will those be able to be handled in an anaerobic digester? Wastewater treatment plants are also very finicky about what they want to treat in their digesters. They've had 100 years of treating the same material. There's a really high comfort factor in that, and breaking that comfort factor by convincing them that, yeah, you can take this slurry material, you can take this organic waste. They're not as comfortable with that yet, at least in the mainstream. There are progressive sites that are looking into it, have done it, but there is cost to come with that. Solid waste that has been slurried or processed for anaerobic digestion inherently will have a higher level of inorganic matter that is certainly not broken down in digestion, and that is going to build up in digesters that need to be cleaned out more often. There's also a potential for increased different and excess odors that will need to be managed. And for certain locales and sites, there is a permitting issue, or could be a permitting issue, by taking in more organics, either because of the perception of it being a solid waste handling or processing facility, potentially greater amounts of biogas to be dealt with from local air quality and air pollution control districts, and then just the regular permitting that wastewater plants go through, dealing with what is inherently a solid waste is something new to them. So they do tend to be more risk adverse and a little more cautious in moving into areas that they're not generally a part of when it comes to permitting. Next slide. So a specific project that the company that I work for, Lystek, we partnered with the Goleta Sanitary District off the coast just north of Santa Barbara, the University of California at Santa Barbara, and we teamed up and we were granted a financial grant from the California Energy Commission to specifically look at how food waste could be received, processed, digested, and the resultant benefits of biogas generation. So you can see on the picture how close the Goleta Sanitary District is to the food source, UCSB. Really a ideal location. And again, that's always not going to be the case when sourcing organic waste. Also, a university does tend to be a little bit more maybe a little more homogeneous in its waste stream than an urban environment. And then the picture on the right is the specific plant location. You can see some large ponds off to the right, and the little red square is where we located our facility, kind of tucked in between a couple of elevated buildings, so it was very well shielded. We were granted the monies in 2016. It was a matching fund grant, and it took us about 1.5 years going through the permitting, which I had mentioned before, getting all of our arrangements worked out. Took us about 9 to 12 months for fabrication of the equipment, and we basically came online in the third quarter of 2019. And I'll give a little bit more about the operational and the results coming up. Next slide. So this is a really nice, I think it's a nice picture of what the facility looked like. You can see it's being erected and put in place. It was a skid mounted, fabricated by a California company. On the far right, you'll see 2 test digesters. They're just over 2,000 gallons each. Behind that is the skid, showing where the Lystek technology resides. There's that thing being highlighted by the cursor is the reactor. That's the Lystek technology in small form, and the other components tend to be a steam unit, some of the process controls, and then they're putting a covering over it. So a nice overview of a really compact site. On the roughly up and down the slides on the left, we had to construct a source separated organic receiving pit. We did have a depackaging unit that we sourced from the Netherlands, specifically for this project, called the Smicon unit, our twin digesters. And at the end, we had our Lystek thermal hydrolysis. Next slide. So what was the feedstock like? The feedstock, in some cases, did look like about a lot of garbage, unfortunately. We were kind of hit with a lot more bags. Our attempt was to get into the dining halls and cafeteria at the school, where we thought we'd have a really nice mix of material. We ended up getting, certainly we got what we asked for. We got a lot of bags of food waste, and with it came a lot of trash. You can see the general components there on the upper right, forks, knives, plastic bottles. But we struggled through that. We made it through it. The Smicon unit ended up producing a very nice slurry material, a little bit more manual labor than we had counted on, having to kind of debag the multiple bagging process that the university went through. But at the end of the day, we did end up with a very good sorted source material. So next one. So a little bit of the interior of what the Smicon unit looks like. It uses a combination of screens, a hammer mill, and kind of a vortex to separate the wetter fractions of organic waste from the plastic. So there's a drum with screens, and it rotates with hammer to break out the material, and it separates it into a slurry material and then a dry or large contaminant fraction that was removed off-site as waste material. Next. So the anaerobic digestion, basically nothing unusual about it. It was a monodigestion. This was not started off as a specific co-digestion of traditional municipal wastewater and the source separate organics. So we were trying to basically maximize what the potential gas yields would be. We saw some very good results, and we saw some very stable results. Basically, anaerobic digestion, whether it's food waste or municipal liquid waste, tends to be very consistent in that low 60% methane range. So a very good quality gas for biogas generated. The yields tended to be what we would expect. You'll see some verbiage here about how we did deal with some sludge and sugar. So one of the parts of why we use sugar is when we started this project in an August time period, school was just opening up. We made it through the fall semester, and then we hit the Christmas and holiday season where the university goes into a very quiet mode. We still needed to keep our digesters healthy, so we had to supplement it with a sugar additive. And then, of course, what came after that in early 2020 was COVID, where the university also shut down, and we had to look for some alternative waste streams, which was not what we had expected, and certainly not the challenge we wanted to see. The other highlights we ran into is we did hit some H2S, hydrogen sulfide peaks, and mostly due to a higher content of red meat. A lot of uneaten hamburgers, believe it or not, at the university. We got stuck with sometimes with a waste stream that was called late night, where students are allowed to go late night, buy a bunch of hamburgers, apparently not eat too many of them, and the rest ends up in the waste. So we had to deal with some unexpected spikes, but maybe not unexpected in the real world either, where you don't have complete control over your source separated organic waste stream. Next. So very quickly, getting into the Lystek portion of the process, where post-digestion, you do end up with a couple of components. I mentioned biogas is one component, but you also have a digestate that does need to be handled. And that can be handled through the Lystek thermal hydrolysis process. It's a three-part concurrent process of heat, a physical shearing, and a pH alkaline adjustment to end up producing a class A kind of end product, multiple end products for fertilizer, or digester enhancement, where you can actually take the material once it's been lysed and feed it back into anaerobic digestion in a co-digestion mode of either municipal waste or food waste, and you'll get a higher, basically overall gas generation amount, and in some cases, depending on the specifics, a higher yield from the waste stream as well. So some of the numbers, we talk about a pH target of about 9.5. The solids the input can be anywhere from a very low single-digit % solids up to the mid-30s. Our target range to meet regulatory requirements is in the low 70 degrees Celsius range, and then there's a time requirement of 20 to 30 minutes. And what basically comes out of it is a very consistent material, very liquid type material. Pumpable, high solid content in the 13 to 14, 15% range, and a very predictable nutrient range, nitrogen, phosphorus, potassium, good nitrogen level, and makes it a very valuable component for agricultural uses. Next slide. So inside the Lystek process, you can see it's a modular unit on the left, a very easy to manage material, the shearing blade, consumable item in some respects. It's about the only moving part in the whole process. And then the end product, agricultural, is a traditional agricultural method of applying it to farms and fields as a soil amendment. And again, a very good source of nutrients, both in the short term and building up healthy soils in agricultural areas. Next slide. So where would a Lystek facility fit in a typical wastewater treatment plant? It does tend to be mostly sourced as a post anaerobic digestion, post dewatered component. And again, that makes the anaerobic digestion process in the wastewater plant less changes need to be made. And then the material has a couple of outlets, so we can send it back as an anaerobic digestion enhancement. It can be in certain cases used as a nutrient removal and in a biological nutrient removal process at wastewater plants. Traditionally, it is used as a soil amendment on an outbound product, which also allows for some economic revenue enhancement as well. So in a complete kind of case study at a wastewater plant, there is an opportunity to offset operating costs with some back-end revenues that in the past would end up being an expense for a lot of landfills, taking their biosolids to maybe a landfill or compost where they're paying for it. Here, there is a cost of making the material, but then there's an opportunity for some revenue enhancement on the backside. Next one. So we also looked at the thermal hydrolysis as a pre-treatment for food waste. So instead of just making a straight slurry through physical processes, we also took it one step further in our project down in Goleta and actually hydrolyzed the material prior to digestion. So what it basically ended up doing was making a better slurry material. So even though the solid content tended to stay about the same, we did tend to make smaller sizes, and smaller sizes are easier for the bugs to eat. So that went very well. We did notice that, again, gas production was over 20% higher because of the thermal hydrolysis process, and our yields also were increased. We also had a lot less volatile asset variability than in a normal digestion process. So overall, we were very happy with that result. And we just yesterday submitted our final report to the California Energy Commission about this project. So we do expect that to come out as a published document in the next few months for those that are interested. Next slide. So looking at graphs, sometimes graphs speak better than words. You can see from the left table what we were projecting to feed material and what the output was of biogas at the higher feed rates. And the refeed rate is based on a dry weight basis. So in the beginning of that left-hand table, where we were feeding back 17% on a dry weight basis, we increased it to 28%, and we saw increased biogas generation. We're now going into the 50% range kind of as we speak, and we do expect even greater benefits from biogas. But also there was, where does the gas come from? It comes from the breakdown of organic material. So as you can see on the right side, the more we feed, the more material, the more solids are broken down, and at the end of the day, the less solids are actually leaving the site. And from another economic advantage, that is very big for wastewater plants to, again, have kind of that double win of I'm taking less solids off site, I'm paying less. I'm also producing more gas where maybe I get paid for that, or I can make some energy out of it. So next. And speaking of next, what is next? Well, we do intend, like I said, we're upping our refeed rate to 50%. That's kind of our target. We think that's an optimal number. That'll be borne out in our study that we're currently doing. We also want to validate that maybe the additional feeding of biosolids back into the thermal hydrolysis process will have some polymer usage reduction. Polymer is a large cost at wastewater plants for digestion, and getting a dewatering process. We think we can reduce the polymer needs, not only through less overall solids, but some of the polymer being returned. And then from the source separated organics, we have the ability at this Goleta plant to increase the overall solid processing and digestion much higher than what's been seen in most plants in the United States, and much more traditional what's been seen over in Europe, where solid content digesters here in the US might range in the 2-3%. We're looking to kick it up to the 5-6, maybe 7%. And then also look for end market alternatives to biogas, both from a straight energy conversion as pipeline gas, transportation fuel, on-site generation. So some good opportunities we look for on that. And with that, thank you for the opportunity to speak for you as a group. I'll take any questions now, or you can hold them off till later.
Actually, Jim, we do have one question here. David Gordon is asking about the beneficial uses of the end product. And that question came in early, so you did address it a bit, but you may want to mention you are producing a Class A product here, right? You've gone through PFRP?
Yeah, correct? We do. We produce a Class A standard US EPA Class A material. And also our product has been registered with the California Department of Food and Ag as a licensed fertilizer. So it basically acts as an alternative to traditional chemical or synthetic fertilizers that farmers would buy.
And it is a liquid, so its transport capacity is minimal, right? You want to get rid of it relatively close to the plant, I'm guessing. I'm thinking about David's question.
What we found from practice is anything within, say, 60 miles of a wastewater plant makes it economical, and that covers quite a bit of ground for most plants.
Good to know. I think that answers David's question. Well, thank you, Jim. If there's any more questions can come up, we can pick that up at the end of the session. Let's give the time now to Tej. As we go there, at those that are watching, remember you can add your comments, your questions in the chat box. And we'll pick those up at the end of the next presentation by Tej. Thank you. Tej?
All right, thank you, Tim, and thank you, Jim. Great presentation. I sort of was reflecting on all these uneaten hamburgers from late at night at the universities or the colleges. I find that one very strange, having spent a long time in university and often being a starving student, so really interesting. So again, I'm Tej Gidda, and I'm sitting up in Canada. I'm in Waterloo, Ontario. And right now, as Tim mentioned originally, I am GHD's global leader for what we call future energy, which I'm not really going to talk about a lot today, but all my background is in the waste business and have been in this for the last 16 years or so. So very interested in anaerobic digestion around the world. I just want to talk about some of our observations around anaerobic digestion and where we see it going. So going to talk about, energy from waste, if we want to call anaerobic digestion energy from waste, what drivers look like in North America versus here in California specifically, and then just how to take a look at different technology. What are the different styles of digestion? How do you pick? And what can you get out of these processes that add value beyond maybe even what we're experiencing right now? All right, so a little bit on sort of, if we want to call it energy from waste or waste energy. I think some people don't like to use that to term or fit out anaerobic digestion. Some people do, somewhat depends on where you are. But I think the point of me putting this slide up here is over years, there's been such an interest in sort of the energy part of this equation. And in my role, where I'm sort of, working with a lot of companies in the energy space who are trying to transform their businesses to reduce emissions, build assets through an environmental social governance lens, the energy landscape is really changing fairly quickly now throughout the world. We're seeing a lot of people set net zero carbon goals. A lot of companies, corporations like GM saying that they won't be producing internal combustion vehicles after 2035. They're moving to electric and hydrogen. So the opportunity for waste to participate in that energy transition is pretty significant. And there's a lot of different ways that can happen. There's a few shown up there on the right. But there's a real place to be played here. And I know we've always sort of talked about waste as a resource that can participate in energy, but really that energy part is more important now than it ever has been, and it's only going to continue as we start putting more and more prices on carbon. So Europe and our friends in Europe, and I've spent a lot of time in Europe, so I'm going to see interesting bits of technology. I think last count there's 20,000 anaerobic digesters in Europe. Anywhere from agricultural digesters to wastewater digesters to dedicated food waste digesters. But you can just see in the graph on the left sort of what our future in North America might look like. If you really look at the Netherlands and Germany, you're seeing very, very little amounts of material that are actually landfilled at all compared to what we are in the US, and Canada is pretty similar. We're about 70% of waste landfill. So the question is how do we go from one bar to the other, and what does that look like? And frankly, how do you monetize that? Because diverting material from a landfill and putting it into these assets is not something that's immediately going to generate a positive business case. It can, but I think in part that will depend on sort of the ability to drive energy out of that final product as people put more and more of a premium on that. There's lots of bits and pieces of energy content in waste, as you can see at the top right, just a typical composition that can be realized. I think the question is how to do it economically, and what technologies and approaches are we going to use. With respect to anaerobic digestion, it's really the food waste component that we're looking at, and the green, the organic component. Sorry, next slide, please. So I think market drivers, the market is changing quickly, as I mentioned before. I think, having done a lot of work in the renewable natural gas space, I think we've all seen how renewable natural gas has really changed the market for what do you do with biogas. There was a time when, I would do a lot of work on converting biogas to electricity, which is tried and true, and we know how to do that, and we know how to do it reliably. But that market really shifted as renewable natural gas came on the market for the simple reason that electrical grids are starting to decarbonize and have over time, but the natural gas grid is still 100% fossil fuel, and there's greenhouse gas emissions associated with it. So really the demand for plugging renewable natural gas into the natural gas distribution and transmission system has become really strong over time. And I think it's a really good example of a pretty quick shift in energy markets. And if I can be bold a little bit here, there is a market demand coming beyond renewable natural gas, and I'm sure most people are across it, and that's the hydrogen market. That market is developing and fairly quickly. It's very active in other parts of the world. I'm involved in hydrogen projects out in Australia, where our company is from. Europe is the hotbed for hydrogen work right now, and there's a natural nexus between waste and hydrogen. So California, I think not everyone on this call is from California, but a number of people are and are very familiar with what SB 1383 really means and what SB 100 really means, getting California to net zero carbon or zero carbon electricity by 2045. That's a really ambitious goal. And there's a lot of work to be done in order to hit something like that. There are other jurisdictions that have similar mandates now. You can see on the left side too in the graph, the notional effect of SB 1383 to divert 20 to 25 million tons per year of organics from landfill by 2025. That's also an incredibly ambitious goal, but it just speaks as to the amount of material that needs to be managed and that can be converted into some form of energy, again, which has more and more of a value the further we go down this route. So picking AD technology, and the reason I'm kind of concentrating on AD is, there was, when I started in this market, I was doing a lot of work on composting and still love composting, still do a lot of composting work. I do it in my backyard and, still involved with a number of municipal and private sector clients that do composting. But there are some advantages to anaerobic digestion that can't be overlooked. If you look at the figure in the middle with the tall, shiny tanks, that's a City of Toronto anaerobic digester. It's a municipal digester that I've been working with on for many years. Part of the reason that plant exists is because it needed to be built in the middle of the city, and we didn't have a lot of footprint. So a nice wet digester system can be really small. That thing is 80,000 tons a year, and it sits on 2 acres in the middle of the city, and it's never had an odor complaint for as long as it's been out there. So, that's a really important pull with respect to siting when you put these things, and just the issues around odor. So the important drivers, but I think the right side of this figure on the biogas, and Jim sort of mentioned yields from Lystek process and sort of how that could work. The yields are really important. I mean, a lot of this comes down to how can we optimize the amount of biogas we're creating to create some kind of beneficial product that we can sell into the market. And we can't ignore the bottom part. Digestion is not going to make material sort of disappear. There still will be a non-digestible component that's going to come out of this process that needs to be managed in some way. And that's often treated as a cost rather than a revenue. So it's important to optimize what that's going to look like. And there are many approaches and some really interesting new ones that have an additional energy advantage to them as well. So just broad classifications, I think, of anaerobic digestion. I think from our standpoint, or my standpoint, pretty ambivalent to having any favorites sort of along the spectrum. I think there are solutions that are going to work along the spectrum for any situation. And it's really about figuring out what your feedstock is, what it looks like, and where you need to fit on this line, plus pairing that up with what do you want out of the process? So wet AD on the left, total solids less than 15%, sure. So you see a little representation down there of a mixed vertical tank that is consistently mixed. So it's got to be a little bit more dilute when you want to put materials in there. And quite frankly, you wouldn't probably ever consider putting green waste into one of these tanks. So if you've got an organic stream or a food waste stream that has a lot of green waste in it, it's very difficult to include it into a system like this. But if you don't, it's a very interesting proposition to use one of these technologies because they're very space efficient, and they produce a fairly large amount of gas. In the middle, you see plug flow digestion. This is fairly common in Europe, and it's becoming more and more common here. And I think we'll see more of this coming into the market because it's a very robust system. It's a really interesting system to deal with organics from municipal solid waste as well. And dry AD on the right side, for those of you who are pretty familiar with in-vessel composting, dry AD is really tunnels, concrete tunnels that are made anaerobic, and then material coming out of those tunnels will then go into some kind of composting piece. That is also fairly common in North America now and definitely has applicability into the market as well. I think there's a fundamental difference between all these. I think when you're doing wet digestion, you have to remove the contaminants first. You have to get everything sort of out before you go into those wet tanks because you don't want things settling at the bottom. Jim had a photo in his presentation of an anaerobic digester with a whole bunch of sediment at the bottom. That's actually a project I worked on where about 20 feet of grit had accumulated at the bottom of a wet tank and completely interrupted the ability of that tank to work. It was a real mess getting rid of all that stuff and restarting the tank. So thank you, Jim, for bringing up some really bad memories there. Really appreciate that. But it's a great example of what could happen. I think plug flow and dry AD have a completely different outlay in that you don't have to remove the contaminants up front. Plastics and all these other things that come with the organics can stay in through the process. The material is removed afterwards, usually put through composting to dry it out, and then you screen out the contaminants. So it's really different from that standpoint, but again, all applicable as long as you understand what the incoming material really is and are respectful of the character of that material. So pre-processing for wet AD, and I just mentioned this because I find it, incredibly interesting what pre-processing for wet AD is. And again, I mentioned that if you're going to use wet AD, you've got to remove the contaminants first. So I sort of categorize it as three main styles of processes out there. The top is extrusion. Extrusion is just nothing but exerting high pressure against the screen to essentially juice the stuff through, or you see a garlic press in there, and that would give you sort of, that's my example, that's how I explain it to my kids of what extrusion of waste really means. It's like a big garlic press. The middle one is pulping, which is like a washing machine. So you're putting stuff in a vat, you're filling full of liquid, and you're moving the screw very, very quickly, and you're basically solubilizing all the material. The bottom one is one of the oldest ones, and it's been around for a long time. And this is what Jim was sort of referencing to when he referenced Smicon as the technology that was being used in the Goleta project. This is hammer milling, which can be used across a variety of different substrates as well. So the real key here, though, is understanding the nature of the incoming feedstock, the organic feedstock, to select one of these systems. I think in general, the rule is the simpler the incoming organic stream, the less robust the pre-processing has to be. The more contaminated that incoming stream, the more robust that system has to be, and the harder it's going to need to work, and the more investment it's going to take to actually remove all that contamination before you get into the wet anaerobic digestion system. Post-processing is really important as well. I think I talked about sort of product and coming out. Liquid digestate as an option, the stuff coming out of a digester being applied on land directly is definitely a possibility, but it's a very dilute product. And if you're going to do it that way, you need to be in proximity to agricultural land where you can actually go on land, and you need to have the regulatory authority to do that. Solid digestate is also very interesting. One of the pinch points that we see in the market is around land application of digestate or even compost. Emerging contaminants are really changing the discussion around this. So PFAS, or per and polyfluoral alkyl substances, and their presence in both biosols and food waste are really altering how I think people ultimately are going to look at going on land with anything that potentially has those components in it. We're trying very hard to get ahead of that. Thermal treatment will help to denature PFAS. Pyrolysis is listed on here. That's one of those options that could be very interesting for that. And pyrolysis, incidentally, is a process that can also generate some hydrogen. So I think this is going to be a field that will evolve, this management of digestate and compost, over time as land application regulations change due to things like PFAS. So novel biogas uses. So the way I like to think of this, and I don't want to go through this whole figure, but obviously if you have biogas, it's a fairly easy pathway to get to renewable natural gas. There are off-the-shelf pieces of equipment following that top pathway that will remove the methane from the carbon dioxide stream, plus other equipment to get rid of hydrogen sulfide, moisture, particulates, all those types of things. And then you have a renewable product that can go into the grid. And that is a really great way of looking at sort of grid, natural gas grid decarbonization. Well, I will say that if you took every biogas source in North America and you added them all up and you thought about how much natural gas you could displace, it's only about 10%. So it's not a dominant factor in decarbonizing the natural gas grid, but it's a very, very important one. Other sort of tweaks that can be made, you can see off the top figure, there's a carbon dioxide stream that's shown. That's what we would call tail gas. That's usually emitted to the atmosphere. One of the really interesting combinations that can happen here is producing hydrogen locally on a site and combining it with that carbon dioxide to produce even more methane. That's a process called methanation. It's very possible. It's expensive, but it's very possible, and it sort of brings hydrogen into the equation while increasing renewable natural gas yields very significantly. So really interesting way of potentially doing it. The other one is just, if you have renewable natural gas, that you can go through that bottom process, steam reforming. That's how we make hydrogen in North America, and we use a lot of hydrogen in North America in industry. If you have methane, you can split the carbon from the hydrogen and you've got your hydrogen, and that hydrogen can then be used in the natural gas distribution and transmission system as a blend with the natural gas that's already in there, as long as you capture the CO2. So it's very powerful to have biogas as a possibility. And to me, this is future proofing. If you can have this and you have that product, there's a real potential to engage in that future hydrogen market. It's not quite here yet, but it is coming, and it's coming fairly quickly. I would imagine the switch will be turned on that in the same way that the renewable natural gas market was sort of switched on a few years ago. So a couple projects. This is one I've been involved in for a long time, so I think it's a great one because of the parties involved. So the City of Toronto is a municipality. It's our biggest municipality up here. It's about 2.8 million people. They do a great job separating food waste from residents. 90% participation in that program at the single family household level, which is great. That food waste goes into a digester. You can see in the top right a little hint of a flame. The gas from that digester has been flared for years and years and years, but that asset in the middle is a renewable natural gas facility owned, operated, financed by a company called Enbridge, which is a very big natural gas transmission and distribution company. So really interesting confluence of how waste is suddenly right on the forefront and discussion point for energy companies as big as Enbridge, which is a fairly large company that is looking to help transition its business over time, because right now its business is 100% dependent on natural gas. So renewable natural gas is very interesting to Enbridge, and this is a great partnership and a great example of a project. Methanation, I talked about this a little bit. We're not involved, I'm not involved in this project, but there's a large project in Quebec, which is our neighboring province up here, where they are taking carbon dioxide off a very large ethanol plant, corn to ethanol plant essentially. And that carbon dioxide is going to be methanated in that same process that I was talking about before to create a value-added product. Essentially renewable natural gas in this case. That project is quite at scale. It's not completed yet, but I think it's a great example of what can be done with even waste streams like carbon dioxide from a renewable natural gas project at smaller scale to increase yields and increase revenues and reduce carbon footprint. Biogas and fuel cells, definitely possible as well. Just an example of how biogas directly with a bit of pretreatment can go through newer age equipment to actually create electricity at a local level. I think that's very important. And I will say, if you have electricity from a renewable source, you also have a potential for participating in that hydrogen future, because clean electricity that's exposed to a water molecule through a process called electrolysis will generate hydrogen and oxygen. And that's a very well-established old process. The trick on that is to make sure your electricity is at fairly low cost, because you're trying to create a lower cost final hydrogen. And to do that, you need a low cost of electricity. My friends in Quebec, our neighboring province, again, electricity costs about 2 cents a kilowatt hour, which means you can make really, really economical green hydrogen that you can sell into the market. This is relatively recent. So we, GHD is a consulting company, but, we are taking positions on technology as well. We just recently invested our time and effort into this company called Lavo. And what you see there is a hydrogen battery. And that particular hydrogen battery is new into the market. It's coming out of Australia. And what it's intended to do is sit in people's houses and be connected to a solar array on a rooftop. And this unit will store electricity for about 3 days for use to buffer peaks and to sell back or to use back for electrical supply. So it holds a lot more energy for a longer duration of time than a battery would. This is a metal hydride technology is what this is, and we've actually chosen to invest in it because we believe in this sort of future of hydrogen and energy storage, which I think is extremely important. So really sort of interesting and very new development. This only was announced a couple weeks ago. In research and development, so my background is in research, and I love research and love new ideas that sort of are coming around and coming into the market. There's a lot of people who are looking at biogas again as a real resource that can be used in a variety of different ways, but organic waste as well. I'm working on a project here in Ontario where we're converting organic waste directly into hydrogen, which bypasses all these other steps in the process. And that would be a really interesting technology, I think, to bring out into the market. So I think this is my last slide. I think this is the really interesting part about this field of anaerobic digestion and the potential for biogas and what you can do with that biogas. There's so many uses for it and so many different ways to drive real revenues, but also carbon value and emissions reductions from doing that as things develop and evolve over time in a very, very large energy transition framework globally. Thank you.
Thank you, Tej. Very interesting. We do have one question teed up here, and it's basically a question that about can you put in OMRI or organic certified compostable consumables into an AD unit, and if so, fiber only or certified compostable plastics. I think you want to go back to your earlier portion of the presentation and address that one if you can.
Yeah, I can. That question gets asked a lot, and I think it's a very pertinent question. And I think it goes back to the different types of digesters. I think if you've got a wet digester and your intent is to remove so-called contaminants before they get into that wet tank, you're probably going to end up removing compostable plastics before they go in there, and they'll probably go out of the facility as part of your residue stream. So there might be a way to circumvent that and short circuit that, but I think it's a difficult discussion because you'll have those plastics mixed with other plastics. The other two options, plug flow and dry AD, I think that's a different discussion. I think compostable plastics would go through these processes from front to back. They may denature a little bit in the digestion step, but I think that's the really interesting part is after these two processes, you need to compost the final material in order to screen out contaminants, non-biodegradable plastics, for example. So I think there's a chance that through that combined process of digestion and composting for plug flow and dry AD, you may be able to denature those compostable plastics and actually turn them into something. We're doing a study here in Ontario where we're actually testing this through different types of technologies to see if that's true. I think for me, you just need to see the data for whether or not it does work or not, which means trialing this and testing these materials through all these different processes.
Thank you. Denature being volatilize, right?
Volatilize, break down, just
Yeah,
break down and turn it into final product.
Thank you. Another question here. Can you go into more detail about the Purdue University project of waste to hydrogen and what's the status currently?
So I don't, so the waste to hydrogen project is the one I'm working on. It's not Purdue, that's here at the University of Waterloo. We are in bench scale testing right now. Bench scale, which kind of looks like what you see on the screen here, has been successful. We have a hydrogen signature. We're now moving into a demonstration scale. My intent is actually, we have a rather large office up here in Waterloo, Ontario, where I sit. The intent is to actually harvest the food waste from the office and build a demonstration project in the back parking lot to actually do this. You probably wouldn't actually use the hydrogen for anything other than flaring it probably, but we just want to demonstrate that we can make the appreciable amounts of hydrogen. I expect by the end of next year, we'll have some really good results, all publishable. It's all going to be publicly available. We're working with universities and through grants to do this work. So it'll all be openly available, and we have really high hopes for this technology.
Interesting. Sounds like it could be a still or maybe a brewery back there. Way to go.
Oh, I like that.
Okay, let's see. One more question. Are Toronto's organics collected by source separated programs, or how does that? Tell us about the collection program.
Yeah, I can do that. So Toronto's a very interesting case study. So again, about 2.8 million people. One half of those people live in single family homes. The other half live in multi-residential. So Toronto's collection system for multi-residential has been pretty unsuccessful, I would say. I think they would say that as well. It's hard to get people to separate organics in multi-res. Their residential program is source separated. It's at the curb. So residents put out green bins full of organic material. Those materials are allowed to be put into plastic bags, grocery bags, for instance. And you're allowed to put diapers and pet waste into that stream as well. So it's what I would call a very convenient system for residents to participate in. But again, to my earlier comments, it means that you need to have an extremely robust pre-processing system to remove those contaminants from the organics. And fortunately, the city has one. They have one plant that's in commissioning right now and another plant that's been operating since July 2014. Full scale the whole time, no issues with downtime. No odor complaints or anything. So again, matching up that pre-processing system to the matrix is really important. So it is a source separation program. It's probably one of the most contaminated organic streams I've ever seen, and but it's manageable and it makes a lot of gas.
Did you say it's in a separate cart from your green waste, or is it? It's a. Could you clarify the cart? What goes in the cart?
So the green bin, as we call it here, is what we associate with the food waste. You're allowed to top that bin up with green waste, but the green waste collection is separate. So it doesn't go into the same bin, and it doesn't go into this digester system, which is a wet digester. So you wouldn't want it in there in large quantities anyway.
So another truck on the road is the short answer then. Yeah.
Another truck on the road. That's right.
Right. Okay. One more question. What is the name of the Australian hydrogen storage cell manufacturer?
So it's Lavo, L-A-V-O. You can kind of see it on that figure, on that module though. There's 4 little letters. It's Lavo.
Okay. Well, we've just wrapped up the hour. Perfect timing. I think we're done. Thank you everyone for participating. Not seeing any more questions. Of course, this will go into a recording. We'll post it on the Gold Rush Chapter website. As always, the next event coming up is going to address construction and demolition on April 9th, and then safety in May, and finally alternative technologies in June. So that's it. Thank you, everyone. Have a great day and a great weekend. Thank you. I know.